Well, YouTubers, welcome to ToobTime. This particular instrument I procured from my favorite electrical auction house. It's a bridge, and this particular bridge can measure LR and C values, inductance, resistance, capacitance, and I got it from my absolute favorite electronic auction site. So this equipment was tested. It had battery, corrosion problems inside, or so it said. I decided, well, let's give it a go and see what happens. You can't have too many bridges. So, take a look at it. You'll see a little overspray on here from somebody spraying something. Oh boy. The back end has a cover where apparently there was a factory blue plate in here, but I would imagine that battery corrosion has consumed that plate, the original plate. So someone made a very nice plate to fit on here. So let's take this off and take a look inside and see how bad the corrosion is. Some of these batteries, I don't know. Seems like batteries nowadays corrode a lot more than they used to. It kind of reminds me of the carbon battery way back when carbon batteries were popular. Okay, so here's a plate that someone had nicely made. And inside, well, it's not that bad in there. I've certainly seen worse. All right, let's give this thing a little power and see what happens. So to power this thing, we're using the Heathkit IP27 that replaced the germanium transistor with a silicon one. It's still chugging along, believe it or not. Okay, we made the positive connection. Now we make the negative connection and hope that it works. Sorry for jiggling the camera. It just gets in my arm just gets in the way, or the camera gets in the way of my arm. I don't know. One of the two things, anyhow. Alrighty, so now we have a positive and negative connection to it. The power supply is in standby, so no power is going in just yet. Alright, let's take a look at the top of this thing and see what we see. Ah, yes, these little snap brackets make you nuts. Oh, what a nice looking bridge. Okay, so what we have here is a DQ meter, which reads out the quality of the capacitor or inductor you have. Range switches. Function switches for L, R, and C, times 1, times 10 for resistor. This is the nulling dial, null meter. There's our detector and gain, and the type of detection we're going to use. Okay, so this is a bridge. And bridges seem to scare everybody. I guess I can understand it. I mean, look at this thing. It's a circuit with diagonal wires, which no one likes to see. Oops, that resistor had a problem. And the way the bridge works, you draw the circuit up, and this is the negative, this is the positive. It doesn't really make any difference, at least for us at this point. And here is your unknown component. In this case, we'll just use a resistor. And this is a variable resistor. And these are fixed. RF1 and R fix 2. So let's redraw the circuit because it's kind of clumsy looking at it this way, and you can redraw it as something as simple as this. There we go. This is RF1. This is RF2. Here's our positive. Here's our negative. And the way the bridge works is that you have two reference fixed resistors, and they're selected by the range switch. This is the variable, LRC variable switch, where you actually dial in the value. That's this fella right here. RF and RF1 and RF2 are determined by this. And here is our resistor that we don't know what it is. And what happens is the null meter is connected right in here. And it's up to 0. What happens is, as you move this around, you're going to try to get it to be equal to this value, what this voltage would be right here. So as you move this voltage around, you have resistors in here, you adjust your voltmeter. When the two are identical, this will read null. If it's too low resistance on one side, the meter kind of moves this way. And if it's too much resistance, too high, it'll move this way. And that's all based on the voltage it's measuring between these two reference points. So I think you can see that if these two resistors equal this RF1, RF2 relationship, we will have we'll have the same voltage here and here, and we will have a no voltage in the top. Okay, that's enough of that nonsense. Let's get on to playing with the thing. Alrighty. Move this out the way for now. Now, bridges, they're all run the same, but they all have a slightly different operating process. And here they have given everyone a cheat sheet that shows how to make your DC resistance, your capacitive resistance, and your inductance measurements. And a little bit of battery information. These are the circuits that it's showing you. This is important. Don't try to use a bridge until you understand how to set it up and run it. I don't know if you could really hurt anything, but you'll certainly confuse yourself in the meantime. So what I have here is a 100K resistor. And this resistor is in a little bit of a holder, lead test holder. And we're going to put this right up here, and this is our resistance under test. So now we'll turn this on slowly. And we got to let this thing warm up a bit because it's got to think about itself. Oops, got to turn on the power supply too first. Come on. Oop. I would lay odds that my battery lead is not making a really good connection. Because this meter should pop up when I turn it on, or should move around a little bit. So let's take a peek inside and see if we're all good with our battery leads. This one looks, maybe it's okay. It's hard to tell with this kind of thing sometimes, whether it's actually touching the part or touching the just plain shorting out. Dang it. All right. Let's see what we got here. Oh boy. Getting a little old for this. You can see the needle moving now, as it should. I almost had a bad connection on the power supply lead. And we'll zoom this in a little more so people can see what's happening here. Okay, so we know, and I'm just using a known 100k ohm resistor. You wouldn't necessarily have to know it. It just makes it easier. Our function is resistance, and it's resistance times 1, because on the resistance scales we have 100k down to 0.1 ohms. So 100k should fit in with that very well. We'll crank this up to 100k. And we'll begin to do some detecting. Now you can see right here that I have 5 point, there's a 5 and a decimal point here, 0, 0, 0. So we're at 500 k ohms, too high. So what I'm going to do is begin to dial it down. And we know that we're high because we're on the high side of the meter if we did not know the value of the component. So now we're going to turn it down. Oh yeah, that's a little better. Notice when I adjust the range, or the gain knob, it moves the meter a little bit more. That's because we are zooming in on the null factor, the null. So now we're at 400k. Now we're at 300k. We're doing really good. Still going down toward the null. Here is 200k. Oh, that's pretty good too. 100k, still a little high, and 0 ohms, which is low, and you can see that it's gone down below the null point. So we're going to crack it back up to 100 k ohms. Now I'm turning the gain up a little bit, and we're going to adjust it for null. And you notice that I know this one is going to be too much adjustment because it's close to 1k, and we're going to just adjust it. Here's exactly 100k precisely. I'll continue to turn the gain up so I can zoom in on the number a little bit better. Now as I'm bringing it in, here's 101, 102, 103, 104, 104 k ohms. I crank it up here, 100.5 k ohms. I got my gain fully up, and we're pretty close to the 0 point. Okay. So we've actually just measured a resistor with our bridge, and it shows to be to 100.4 k ohms. How close is it? Well, let's check it against our fluke and see if we're close. Here's a nice little fluke meter. We'll turn it on the ohms. Now what I'm going to do is turn the gain down before I fool with it, because I don't want to bang the meter very badly one way or the other. So I've pulled this out, and we're going to stick it in here, and we're going to see we're coming in 100.5. So this thing said 100.4, and I'm very happy with that. Because when you look at this, you know that, isn't that nice? You're reading a number. You know on this, the last digit's always suspect, plus or minus 1. So really, we're bang on. This says 100.4, this says 100.5. I'm happy with that. So what we've done is, this resistor now could be a standard resistor, because we know it's 100.45. We'll split the difference. Okay, so that's a simple bridge. The knobs, from what I can tell, they need a bit cleaning inside. A little bit of contact cleaner. And yes, here we have a very nice bridge. It is an ESI, Electro Scientific Industries, impedance bridge, 250 DE. So, here we go. What do we have? Photobombing our session here is Hunter the cat. He's testing to make sure that I'm doing things correctly. Okay, that's it for now, Tube Timers. I hope you enjoy this little micro segment. This is a Tube Time Sidetrack. And if you like it, please hit subscribe. And if you even like it more, hit the thumbs up button. No, hit the thumbs up button if you like it, and subscribe if you really like it. After this one, we're going to go back to our 6P1 Chinese amplifier. I've made the modifications that I intend to make, and we can go over it and see how she runs. We'll probably be doing that next week sometime. All right, YouTubers, thank you for watching, and everyone take care. Bye now.